Hi ladies, in this video I'm going to go over circular functions, including reference angles, how they relate to the unit circle, degrees and radians, and also touch on the sine graph and the cosine graph. So no notes to start off with. I'm going to develop the notes as we go. So I'm going to start off with the reference angle 45 degrees. Okay, so with trig functions, we kind of use the reference angles 30, 45, and 60. The main reason for that, and if you're thinking, oh, why were they chosen? It's mostly because we can get exact values from these, and also they relate quite nicely to the radians. So radians we refer to, so 45 degrees is pi on 4, 30 degrees is pi on 6. What else do we have? So 60 degrees is pi on 3. So kind of they're just chosen because they work quite well. Now, obviously you can have other angles. So like you can have 16 degrees and you can convert them into radians as well. But we're looking for exact values. So things have to stay whole. And 30, 45, and 60 just mean we can keep things nice and exact. Okay. So the reference angle 45 degrees we're going to deal with first, and we'll then look at the reference angle 30 degrees and the reference angle 60 degrees. Now, our exact values for 45 degrees come from the unit circle. So I'm going to look at the unit circle first in degrees, and then I'll talk about radians. So let's just put everything on. And I haven't put the degree symbol on because I always forget, but they are in degrees. Now, 45, if we just go halfway here, is there, 45. Okay, your reference angle always goes from 0. And remember, your unit circle goes in an anti-clockwise direction. So there's 45 degrees. Now we can actually form this into a triangle. So if I put a line down here and a line across here, and I'm going to take out that triangle. All right, so there it is. This is 45 degrees here. Now this is an isosceles triangle, so the angle up the top here is also 45. But I'm going to just remove that because when we label our opposite and adjacent sides, I don't want to confuse anyone. Now, our hypotenuse, remember in your unit circle, it's a radius of 1. So our hypotenuse in this case is 1. Now, we don't know what these other two sides are. Well, we do if you've done a little bit of work so far, but I'm going to call them x just to show you where these values come from. Okay, so you may remember Pythagoras' theorem, a squared plus b squared equals c squared. So we can find out these values of x just using Pythagoras' theorem. So my two sides, a and b, are both x, and c is 1, so 1 squared. So I've got 2x squared equals 1. Then x squared equals, if I divide both sides by 2, a half. And then x on its own, we're going to take the square root. So the square root of a half gives me 1 on root 2. So in my triangle, actually I might keep not deleted anything. We've got 1 on root 2 here and 1 on root 2. Whoops, got the square root sign, root 2 there. Now, it's a bit weird leaving the your numerator as a surd. So we tend to what we call rationalize the denominator. So to rationalize the denominator, we just multiply by root 2 on 2. Sorry, root 2 on root 2. I always do that because it's, yeah, the final answer is going to be root 2 on 2. So 1 times root 2 is root 2. And then root 2 times root 2 gives you the square root of 4, which is the square root of 2 on 2. Okay, Now, on my triangle, I might just go back and replace them just so I don't have it too messy. Then we've got √2 on 2. Now, there's our basic triangle for the 45-degree reference angle. All right, so we can use this triangle. Now, it is looking slightly different to how it would be written in your textbook, and I'll explain that in a little bit more detail in a second. So I'm going to just stick with the √2 on 2, √2 on 2, and the 1, but if you've already compared it to previous notes or in your textbook, you'll notice that they're different. Okay, with triangles, you can have similar, as long as your angles inside the triangle are the same, you can have similar triangles. So this triangle can be enlarged or reduced in size. As long as those angles are the same, your side lengths will be in the same ratio. So I'll talk about that in a second. All right, so I might need to decrease this a little. Whoops. Let's just make you smaller. Okay, just so I can go on and do, come on. All right, so now we look at our exact values. So we've got to use SOHCAHTOA. So remember, we use our trig ratios when we have a right angle triangle. So this is a right angle triangle that's come from the unit circle with a reference angle of 40 degrees. So let's look at sine first. So sine theta equals opposite over hypotenuse. Now in this triangle that I had over here, you've got theta is 45 degrees, so sine 45. Your opposite side is √2 on 2, and your hypotenuse is 1. So basically anything divided by 1 is just left as it is. So sine 45 is √2 on 2. Now let's move on and do cos. So cos, using our trig ratios, cos theta equals adjacent over hypotenuse. So now we've got cos 45 equals, the adjacent side is √2 on 2 also, over 1, and it's because it's a isosceles triangle. So cos 45 is also √2 on 2. So these are your exact values, and I'll explain what that actually represents in a second. All right, and then lastly, tan theta equals opposite over adjacent. So tan, whoops, let me just write 45. All right, your opposite side is √2 on 2. And your adjacent side is also √2 on 2. So when we're dividing a number by the same number, it's just 1. Okay, so that's 45 degrees, your reference angle 45 degrees. Now, if you want to do the radian equivalent, we need to do a conversion. So I'm just going to put the conversion on. So when we go from degrees to radians, and I might just put the whole thing on, we multiply by pi on 180, and when we go the other way, we multiply by 180 over pi. So for 45 degrees, we multiply by pi over 180, and that gives us pi on 4. So basically what we have just done up here in pink, you can replace all the 45s with pi on 4. Okay, so might just write that over on the side here. So sine pi on 4 is equal to √2 on 2. Cos pi on 4 is also equal to √2 on 2. And tan pi on 4 is equal to 1. Okay, so the 45 is in degrees and pi on 4 is in radians, two different measures of angle. Now, you will eventually move straight into radian when you do methods, but it's a good idea to understand how they both relate to each other. All right, now, before I move on to the next bit, I'm just going to upload a picture. Okay, so I've got the sine graph and the cosine graph here. So I might, just because I can't fit both of them on the screen at the same time, you'll notice they look kind of similar. Okay, if you were to look at them from a distance, you probably think, oh, they're the same. But the sine graph, which is this first one, and I might write that up the top because it doesn't actually say it on there. So this is your sine graph. So this is y equals sine x. It starts at 0. Okay, so I might just get a different color. Okay, it starts here. And we have a full rotation to 360 or 2 pi. Now this diagram I've just taken from the internet. I tried to get one that had both degrees and radian on it. Now, as you can see on the x-axis, we have our degrees, but they're associated radian values. So 30 degrees is pi on 6, 60 degrees, pi on 3, and so on and so on. Now, we're currently doing 45 degrees. So 45 degrees hasn't been written on here. I couldn't find one, but I got 90 degrees. So I know 45 degrees is about halfway there. So there's 45 degrees, or pi on 4. So basically what sine of 45 is we go up on our graph and then we go across to here. Now we can't really read that too well on this graph because we don't have a scale, but it's just to show you, well, what these values actually mean. So they actually relate to something. So if I put it on my calculator, and I've had quite a bit on there already, but if I do sine of 45, now it's probably going to give me, oh no, it gave me an approximate value. It's 0.707, okay, which is the same as the square root of 2 on 2, okay? So square root of 2 on 2 is your exact value, but your decimal answer is approximately 0.7. And you can see that on our scale, okay? If you think about 1 up the top, this looks like it's about 0.7, which we know is also root 2 on 2. Now, if we go to our cosine graph, it's not as detailed. Took it from the same website, but it's not as detailed as the previous one, but we've still got the degrees and radian on there. Your cosine and your sine graphs do continue on forever unless you restrict them. So you can see here it's a little bit different with the cosine graph. It started at -90 and it's going to 450, but we can deal with that. Okay, so 45 degrees is here, halfway between 0 and 90, and its radian is pi on 4. So if we go up here, hit our cosine graph, and then go across, you can see, again, it's at approximately 0.7, which is root 2 on 2. Now, when I think about the reference angle is always in your first quadrant from 0 to 90 degrees. But we do actually have other solutions. So if I go across here, like this, everywhere that line hits, I'm going to have the same solution as 45 degrees. So it hits it here and it hits it here. Okay, so I'm going to show you how to get those values in a second. And we can also do the negative value. So if I go down to here for negative 0.7, because remember in your unit circle, sine is both positive and negative depending on which quadrant you're in. So if we go down here, now this doesn't mean negative 45 degrees. Okay, I'll explain in a second. So we're basically hitting our graph 4 times. And each time we're hitting the quadrant. So we're hitting here. This is quadrant 1. This is your value for quadrant 2, quadrant 3, and quadrant 4. Okay, so if I go back up here, just because I've got a bit of space, draw the unit circle again. Here's quadrant 1. Remember, we go in an anti-clockwise direction. Quadrant 4, and I might make the screen a bit bigger because it's going to get too messy from my writing. Okay, so we did 45 degrees. So I'm going to put in my 0, 90, 180, 270, and then back to 360. And you can do the equivalent for radians if you wanted to, but we'll just stick with degrees for now. And I'll do the conversion in a second. Okay, so got the first one. So sine 45. We know that is equal to root 2 on 2. Then our next angle, which is here. Actually, I might do that in a different color. Okay, so that angle there, and I'm just doing sine at the moment, is 180 minus 45. Okay, so we're using the same reference angle. So because we're using the same reference angle, it's going to be still root 2 on 2, and then you decide whether it's positive or negative. So it's writing on my thing again. So in quadrant 1, they're all positive. In quadrant 2, only sine is positive. In quadrant 3, tan is positive. And in quadrant 4, cos is positive. So for my sine 180 minus 45, which I probably should write. So sine 180 minus 45 is 135. It's a positive. You don't need to write the positive in there, but I will. So root 2 on 2. Then we can do the next quadrant. So we'll keep moving around, just choose a different color. We always go from the horizontal. So this green is going to be sine 180 plus 45. And again, it's going to be root 2 on 2. But because we're in the third quadrant, where sine is negative, only tan is positive, it's going to be negative root 2 on 2. So I'm just going to rewrite that. So 180 plus 45 is 225, is negative root 2 on 2. And let's do the last quadrant. I'll do that in yellow. So we've got sine, this time we're going 360 minus, well, it's a bit hard to see the yellow, sorry. Okay, again, it's still root 2 on 2 because we're using the same reference angle, and the triangles are all the same. Okay, so if you're wondering why it's always root 2 on 2, because we're creating 4 of the same triangles. They're just in different quadrants. Okay, and in the fourth quadrant, sine is negative, so it's negative root 2 on 2. And I just have enough space down the bottom to write that angle. So 360 minus 45 is 315, is negative root 2 on 2. Now you can write the associated radian. Okay, so let's just quickly do that over here. So sine, I've already done sine of pi on 4. So sine 135 is equal to, now you can, I'm just trying to think if we're going to do the same conversion. Actually, I might do it. There's a few ways you can do it. I might just do it the conversion way. It's going to do it the other way, but okay. So if we're converting 135 degrees to radians, we multiply by pi on 180, which is going to test my memory. I might just do them all first. So 225, and then I'm going to cheat and do it on the calculator. I'm just wary. Actually, I can do it because 45 degrees is your common factor. So we should be able to do them all without the calculator. It's just early in the morning, girls, and I was just doubting myself. Okay. So we're basically simplifying this fraction. So 135 pi over 180. So how many times does 45 degrees go into 135? It's 3. So 3 pi on 4. 225 degrees, so 225 pi on 180. Whoops. Sorry, 45 degrees goes into 225 5 times, so it's 5 pi on 4, and then 315 pi on 180. We have, oh my gosh, let me just keep thinking, 7 pi on 4. Okay, so there's your radian conversion. Now, for cos and tan, okay, you can do the same thing. Actually, before I talk about that, let's just scroll down here. So what I highlighted in purple are these values. So in quadrant 1, we had root 2 on 2. Here's root 2 on 2 for quadrant 2. So see how they're both in the positive? They're both above the x-axis. They're positive because y is equal to sine x. Or your function is y equals sine x. So we're in the positive part of our graph. And then in quadrant 3, it was negative root 2 on 2. And quadrant 4, negative root 2 on 2. And you can see there we're below the x-axis. So we're in the negative y. Okay, so for cos and for tan, you can do the same thing. Okay, and I'm not going to go through and do them all just because I want to keep the video relatively short. But with your cosine graph, you can see, actually I might just highlight here. All right, there's your first solution and your second solution is roughly here. And then if we were to do negative 0.7, it goes kind of through here. You can see your other two solutions here. So they're your quadrants. So quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay, so you can see how cos is positive in your first quadrant, and then we go below the axis. Cos is negative in quadrant 2 and quadrant 3, and then positive again in quadrant 4. All right, so you can do the same thing with the triangle for 30 degrees and 60 degrees. So remember we started with, let me just scroll back up here where we first began, the reference angle of 45 degrees. So you can do 30 degrees and you can do 60 degrees as well. But I might do them in a separate video just because I know it's already 22 minutes. All right, thanks girls, bye.